Hello everyone. So in this video we're going to be solving question 3 of the AP Physics 1 2018 exam. So this is free response question number 3. So let's read the question. The disk shown above spins about the axle at its center. A student's experiments reveal that while the disk is spinning, friction between the axle and the disk exerts a constant torque. So this will be bit crucial, constant torque on the disk. At time t equals 0, the disk has an initial counterclockwise, which means positive, angular velocity omega naught. The disk later comes to rest at time equals t1. So part A, 1. On the grid at the left below, sketch a graph that could represent the disk's angular velocity as a function of time t from t equals 0 until the disk comes to rest at t equals t1. Okay, so constant torque. What does constant torque mean? So torque is directly proportional. So torque is directly proportional to angular acceleration. So if torque is constant, then angular acceleration must be constant. So we know the graph of angular velocity must be a straight line, no curve. And it must also be like downward. It shouldn't be constant. It should not be horizontal because there's an angular acceleration caused by the torque from friction. So we start here at omega naught. Okay. So it should come to rest at time t equals 1. Okay, so the graph would look something like this. Okay, a constant decrease in angular velocity until it finally comes to rest at time t1. Okay, the angular acceleration, well, we just said torque is constant. That means angular acceleration is also constant from Newton's second law for rotation. Okay, so pretend this is some angular acceleration we're experiencing. Remember, this must be negative. The change is negative because it's slowing the disk down. So the change must be negative. So angular acceleration must be negative. Notice that the slope of the angular velocity graph is negative. So that corresponds that the angular acceleration must be negative as well. Okay? So we have an angular acceleration over here until right here. Okay, not super straight, but yeah, you get the idea. Then it becomes like 0 right here. So just a straight line below the x-axis, or in this case you could say the t-axis, and a horizontal line to show it's constant. So part B. The magnitude of the frictional torque exerted on the disk is tau naught. Derive an equation for the rotational inertia I of the disk in terms of tau naught, omega naught, T1, and physical constants as appropriate. Okay. So we know that torque, sigma tau, the net torque equals I alpha. Okay, but we're not given alpha. We're given omega naught and T1. So here is where those rotational kinematics equations come into some good use. Okay, so we're given that omega F equals omega naught plus alpha T. Okay? So omega final is 0. Okay? So we have negative omega naught. So you subtract omega naught from both sides. But angular acceleration is also negative. So we can just put a negative sign here. In fact, we should put a negative minus sign here because to signify that angular acceleration is negative and it's slowing it down. So that'll be plus negative or just a minus. Okay? And we'll just put a T1 here. So if you divide out both sides by negative t1, we get alpha equals omega naught over t1. Okay, so we have our frictional torque, which is the only torque acting on it, equals I times omega naught over t1. You can multiply both sides by t1 over omega naught, the reciprocal of omega naught over t1, to cancel out all the stuff on the right, and to solve for I, and we get I equals tau naught t1 over omega naught. And there we go. We just got our I. So yes, and it's in all the given quantities. So we basically solved this part B. So in part C, in another experiment, the disk again has an initial positive angular velocity omega naught at time t equals 0. At time t equals 1/2 t1, the student starts dripping oil on the contact surface between the axle and the disk to reduce the friction. As time passes, more and more oil reaches that contact surface, reducing the friction even further. On the grid at the left below, sketch a graph that could represent the disk's angular velocity as a function of time from t equals 0 to t equals t1, which is the time at which the disk came to rest in part A. So at half t1, it will do the same behavior as it did in the first graph. So it will have a constant decrease in angular velocity. Okay. But then once you start adding the oil, well, it will start to curve a little bit. Why? Because, well, that was not much of a curve, I'm sorry. So it should start to curve a little bit. Okay? Towards 0. Towards a constant, like, almost to 0. Okay? Why? Because torque naught, their frictional torque, is decreasing. That means angular acceleration must also be decreasing. Remember, torque is directly proportional to angular acceleration. So if angular acceleration is decreasing, the velocity is getting more and more closer to a constant value. And closer, so the graph should be closer and closer to becoming a flat line. However, there's still just a little bit of frictional torque still there. So it'll start to curve more and more and more towards 0. It should approach 0 as it slows down, but just there's the frictional torque is getting reduced, and it should approach 0, but never actually like be 0, because there's always friction. It's just approaching 0. Same thing with angular acceleration. There's this positive value, right? Negative value, I'm sorry. There's this negative value over here, and it's constant. But once you start dripping oil, right? Once you start dripping oil, the angular acceleration will start to approach 0. So it'll approach 0. Why? Because think about it. If torque is decreasing, okay? So if torque is decreasing, it will start to decrease, but it will never actually decrease because more and more oil. So it is decreasing, but it'll start to get flat over here. It'll start to get flat over here because there's still just a tiny bit of angular acceleration. It will never actually reach 0 until like an infinite time later. So it'll approach 0. And it'll approach it will approach 0, but it will keep on curving towards 0. So that's what this will look like. So part D. The student is trying to mathematically model the magnitude tau of the torque exerted by the axle on the disc when the oil is present at times t is greater than half t1. The student writes down the following two equations, each of which includes a positive constant, C1 or C2, with appropriate units. So you have equation 1 and equation 2 written right here. Which equation better mathematically models this experiment? Okay, so we're going to have to use our graphs for this. Okay, so let's look at equation 1. Tau equals C1 times the quantity T minus half T1. Okay, so if you go just above half T1, okay, so just a little bit above half T1, then this quantity will be very small. Will be very small. That means torque will be very small after T, right after 1/2 T1. Okay, but that's not what it says on the graph for angular acceleration. Remember, angular acceleration will behave just like the graph for torque because they're both directly proportional. So their relationships on how they increase or decrease will be the same. So if torque is very small, that means angular acceleration must be near 0. And as you can see here, clearly it is not 0 right here. It'll just gradually be decreasing until it gets to 0. So equation 1 is out. That leaves us with equation 2. So why is it equation 2? Okay, so if we do right after 1/2 T1, so we'll get some number, okay? Some number divided by the constant will be the torque. Okay, but as you get higher and higher and higher, so as like torque goes to infinity, okay, so time, I'm sorry, did I say torque? It's time. So as time approaches infinity, time will be so huge, t will be so huge that 1/2 T1 will not even have to matter anymore. Okay, so you have C2 divided by a seemingly huge amount. So C2 by a huge amount, the torque will start to get closer and closer to 0 as you divide by larger and larger and larger numbers. So torque will approach 0. Okay? And that's exactly what it says in the angular acceleration graph. So that equation 2 better mathematically models the experiment. Okay? So as t becomes larger and larger, so as t becomes larger and larger and larger, then the torque will, I'm just using the abbreviations, okay, because there's not much space, will approach 0. And since torque is directly proportional to angular acceleration will approach 0. Just using lots of abbreviations, so because there's not much space, but this is what you should write in like full words, which is shown by the graph. Okay, and why isn't it equation 1? That is because, well, actually, equation 1, what's even worse, about equation 1. It predicts an increase in torque. As t becomes larger and larger and larger, then the 1/2 t1 will start to get more and less significant, and you'll be multiplying by a larger and larger and larger number. So equation 1 predicts an increase in frictional torque, And that just isn't plausible, because if you look at the angular acceleration graph, if there's an increase in torque, then the graph should have been moving more downward. It would the magnitude of the angular acceleration would increase. The magnitude, right? But it's a decrease in torque. It's approaching towards 0. You might think straight line means an increase in torque. No, because it's a decrease in the magnitude of the torque. See, this is negative. It's becoming less and less negative. It is going to 0, which means torque must be decreasing. The magnitude of the torque must be decreasing. So equation 1 cannot be correct. It predicts an increase in torque, and right after that, it says that the torque starts at 0 and starts increasing, rather than torque is at some fixed value and starts decreasing, approaches 0. So equation 2 must be correct. Okay, so we just solved this question 3 in about 17 minutes, or almost 17 minutes. So that's good. If you just think about how torque and angular acceleration apply and use a little algebra 2 stuff and how you analyze a graph, you could solve this question. Is really not that hard. If you have any questions, just comment below. Thank you for watching.